Welcome to Power Electronics Education Electronic Book, Lecture 2, Power Switches. This lecture is presented by Dr. FIRUZ ZARE. So finally, when we design the AC drive system, then at the last stage we need to design EMI filter. At this stage we like to have less EMI problem. So that means if we consider everything at the beginning stage of a design, that means we can improve the system, and at the last stage we have less problem to reduce EMI noise. So it's quite important to communicate with each other and then to consider these three factors: losses, harmonics, EMI, because these factors are quite important, because some of the factors which can affect are switching losses, switching speed, which create DVDT and DIDT, and also stray components such as stray capacitor or stray inductor. So these are quite important when we design, and if we can optimize these factors, these parameters, that means we can optimize the system based on these three factors: losses, harmonics, and EMI. So let's look at these three main factors: losses, harmonics, and EMI, based on these two parameters: switching frequency and also the DVDT and DIDT. So what we need basically when we design a power electronic systems, the hardware section is how to define a good switching frequency and how to define a good switching time, which defines DVDT and DIDT. Here we can see that changing DVDT and DIDT, or changing the switching frequency, may affect losses, and we have found that by increasing losses or changing losses we may change efficiency. More losses means more thermal problem, and in this case we need to have heatsink, which increase the cost, size, and weight of the system, and more temperature means reliability problem, and in this case packaging problem, because we need to design heatsink. In some applications, if switching time or switching cycle is much longer than transient time, so the effect of DVDT and DIDT on harmonic contents is negligible, except at very high switching frequencies. So that's why we can see that switching frequency can affect harmonics, can change harmonics. For example, at very high switching frequency we may have less harmonics, but the drawback is more losses. So let's concentrate on switching frequency. So by changing switching frequency we may increase or decrease the harmonics. So in this case the size of passive components is changed. So that means at high switching frequency we need small components as passive components for EMI or line filters. And also we can control and change the ripple on output voltage or current. That means increasing the switching frequency means that we can have less ripple on output voltage or current. And also increasing the switching frequency means that we can decrease the harmonics in output current, and then we can decrease the losses associated with the core losses in inductor or in transformer. But again we have to consider again here that increasing the switching frequency can increase the losses. So it's not easy to define a switching frequency, or it's not easy to increase the switching frequency if we just concentrate on harmonics, because if you just concentrate on harmonics we may increase the losses and also other issues. So the last factor is EMI. So basically EMI can be affected by switching frequency and also DVDT or DIDT. So in one application, I would like to highlight the problem associated with switching frequency. For example, in switch mode power supply, basically in some applications we like to increase the switching frequency. So if switching frequency is above, for example, 50 kilohertz, so what's happened, the third sideband will be around 150 kilohertz, which basically is in the range of EMI. So that's why in some applications when switching frequency is pretty high, we may have EMI problem because of switching frequency. And in some applications, because of significant capacitive coupling, especially in AC motor drive system, so we may have significant leakage current. And in some applications when we have significant stray inductance, because of the IDT, we may have significant overvoltage. So these are the issues that we need to consider when we design a power electronic system. There are different types of power switches. For example, diode, BGT or power BGT, IGBT, Mosfet, GTO, and thyristor. We'll look at all switches and describe in which topology we can use these power switches. BGT is a current control device which needs a sufficiently large base current to turn on the transistor, and the base current must be supplied continuously to keep it in the on state. So basically the switching losses is significant, and the reason is that the turn off time is very long, and also because of a special gate drive to supply continuous current. So that's why this type of switch is not very common in modern power electronic systems. The next switch is GTO. So this switch is a controllable switch which can block negative voltage as well. It can handle large voltage up to few kilovolts, and also large current up to a few kiloamps. So this is a good switch. This is a good power switch for power system applications, but the problem is that the maximum switching speed is around 20 up to 30 microsecond, and in this case, because it's a good switch for high power applications, so it's a good candidate for high power motor drive systems, for tractions, and also active and reactive power control used in power system, especially in distributed generations, renewable energy systems. So in modern power electronic systems, these are the important power switches, which is power diode, power Mosfet, IGBT, and also SCR or thyristor. So what's happened, we normally use SCR in very high voltage, high power applications, especially in power system, or in very low power AC systems, for example, for very simple and cheap AC drive, AC motor drive. So we can concentrate on these four switches: SCR, Mosfet, IGBT is a very good switch for high voltage applications, and diodes for different applications, for example line, rectifier, or converters. Power diodes. A diode is an uncontrolled switch. That means the switch is turned on and off based on its current and voltage. So once the voltage across the diode is getting positive, so in this case diode actually conducts, and the current through the diode depends on load impedance, because in this case normally diode, for example, look at this simple circuit. If you have a diode which is connected to a resistive load, So in this case, if we have, for example, AC voltage, so once we have positive voltage across the diode, when diode conducts, so basically the voltage across the diode, suppose, is very low or almost zero. So in this case, the input voltage appears across the load. So load impedance, if for example is resistive load, load impedance defines the current through the diode. So when the voltage across the diode is getting negative, so in this case diode blocks, that means in this region the current through the diode is almost zero, or leakage current. So that's why we can see that diode conducts in this quadrant. That means it can conduct positive current when it turns on, and it can block negative voltage when it's off. When a diode is switched off, energy stored between p-n junction must be discharged in order to block the voltage and current. So the electric charge stored between the p-n junction and the time to discharge it are called reverse recovery charge and reverse recovery time, which affect switching speed, losses, and EMI. So basically we can calculate this charge, which is QRR. If you look at this triangle, we can calculate this area, which defines the total charge. So if this is the peak of current, which is called IRR, maximum reverse recovery current, so this area equals to current times of time, which is basically in this triangle this side, divided by 2. And in this case we can calculate the reverse recovery charge. We can classify diodes into Schottky diode, which have low forward voltage and they are very fast. So a main drawback is that they are not available at high voltage, so they cannot block high voltage. So the next type is fast recovery diodes, which are used in most modern power converters, especially in inverters, and they can handle few kilovolts. And the next type is line frequency diodes, which can block high voltage up to several kilovolts and handle current up to several kiloamps, but reverse recovery time is long compared to other types of diodes, and there are suitable power diodes for operating at 50-60 Hz, for example operating at line frequency, especially in AC, DC rectifiers. SCR, or silicon control rectifier, or thyristor. This is a special power switch which was very common in the past, but at the moment in modern power electronics we normally use these type of switches at very high voltage applications or very high current applications, because they can handle high voltage and deliver high current. So basically we can use them in HVDC system, high voltage DC system, or we can use them in low power AC/AC converters, in which a simple and cheap converter is required. So a thyristor basically operates when we apply gate signal. A thyristor can be turned on, but we cannot turn off the switch by applying gate signal. So this is a special switch. That means turn on is controlled, but turn off depends on the thyristor current and also the voltage across the thyristor. Suppose that the input voltage is an AC type, and how we can turn on a thyristor in this simple circuit. So basically, over first half a cycle, because the input voltage is positive, then the current through the resistor is 0. So in this case the voltage across the thyristor is positive. So now we can apply gate signal. So by applying gate signal, then we can turn on the thyristor. So once we turn on the thyristor, that means the current through the thyristor depends on this resistor, and at the end of this cycle, first half a cycle, because the voltage actually goes to 0, so that means current through the thyristor is 0. So in this case the thyristor is getting off. So in this case thyristor cannot operate in the second half a cycle. Let's look at current voltage characteristic of a thyristor. So basically thyristor can block negative voltage, and also it can block positive voltage. That means if we don't apply gate signal, so it can stand at that positive voltage, but once we apply gate signal, the thyristor actually turns on. So we call latching current, which is defined by IL, and also holding current. Latching current means that when the thyristor is getting on, the current through the thyristor, when we remove the gate signal, should be more than latching current. So if the current through the thyristor is less than that one, then the thyristor is getting off. And in any case, in any circumstances, when the system is operating, when thyristor is conducting, then if the current through the thyristor is getting less than holding current, so thyristor is getting off. How to turn off a thyristor? Basically, to turn off a thyristor, we have to notice that the thyristor is not a full control switch. That means we can turn on a thyristor by applying gate signal, but we cannot turn off a thyristor by removing the gate signal. So there are two methods that we can turn off a thyristor. One is using auxiliary device, auxiliary circuit. That means, for example, providing negative voltage across the thyristor and also bypassing the current through this auxiliary circuit. So in this case, the current through the thyristor is decreased, and once the current through the thyristor is getting less than holding current, then thyristor will be off. But we have to also notice that because there are PN junctions, we have to consider reverse recovery time. That means the charge between the PN junctions must be discharged, the electric charge must be discharged. Otherwise, if we apply positive voltage, we may turn on the thyristor again. The other point is that in some AC-DC converters, because the line voltage is AC, and if we use thyristors, so the point is that because the line voltage is getting negative in the second half a cycle here, then the current through the thyristor may be decreased, especially when we have resistive load or inductive resistive load. So this is another way, natural commutation. That means that the current through the thyristor can be decreased and the thyristor can be turned off. When we design a power electronic circuit with thyristors, we have to control the voltage stress across the thyristor. That means we have to control DVDT. Because a thyristor is a 4-layer device, we can consider that one as 2 transistors in this configuration. The first transistor is PNP transistor. So if we split these junctions, these layers. Then this correspond to PNP transistor, and this NPN correspond to this transistor. So here we have base emitter in this BGT, that means base emitter, and here we have emitter base, which is basically this junction. So when we have positive voltage across the thyristor, then if we have significant dividity, which happens because of any other switching, because of any transient, and if this transient happens across the switch, across the thyristor, because of this stray capacitance exists between N and P, which means this capacitor. So basically in this configuration, when we look at anode and cathode, because of this voltage drop which is negligible, this voltage drop which is negligible, so if we have significant dividity because of this capacitive coupling, we may have significant leakage current, and this leakage current can be defined as a gate current which may turn on the thyristor. So that's why when we have a power electronic circuit, and if there is, for example, a thyristor in this circuit, so we have to be sure that by turning on and turning off the other devices in this power converter, the voltage across the thyristor has less stress. Otherwise, as I mentioned before here, we may have significant leakage current, and that significant leakage current can turn on the thyristor. There are different types of thyristors. Phase control thyristor is a good switch to operate at very high power, very high current, and very high voltage. So that's why we can use this type of thyristor in power system applications. The next type of switch is light activated thyristors, which can be used in high voltage applications as well, because we have galvanic isolation and we don't need to have a special gate drive when they operate in high voltage. And the next one is low voltage, low power thyristors for light intensity control or dimmer, or any other AC converter operating at line frequency, suitable for cheap AC motor drives. Let's concentrate on control switches. Mosfet is a control switch. That means we can turn on the switch by applying gate signal and is voltage control, and when we remove the gate signal, the Mosfet is getting off. So Mosfet is a very fast switch, and turn on and turn off time are very short. It can be around 100 nanoseconds. And the point is that when a Mosfet is getting on, the conduction loss depends on turn on resistor. So that's why at high voltage this resistor is getting high, so it's not a suitable switch for very high voltage application because the total loss will be high.